Hello and good evening. Thank you for coming to this class. In this class, I will talk about numerical methods. We will be looking at a number of numerical methods to solve equations that we frequently encounter in engineering. Okay, so in this particular class, I will look at solving systems of linear equations using Gaussian elimination method. In this class, we will look at how to solve three types of equations. The first one is the system of linear equations. The second type is the first order and second order ordinary differential equations. And then lastly, we will look at methods to solve partial differential equations. In this class, we will look at a number of different algorithms or numerical methods, as we call it, to solve the three different types of equations that we just saw. These are Gaussian elimination, LU decomposition, commonly called the direct method to solve systems of linear equations. Next, we will look at Gauss Seidel, Jacobi, and SOR methods. Now, this third method, the Gauss Seidel, Jacobi, and SOR methods, are frequently called the iterative method as opposed to direct method. Okay, when we talk about iterative, it means that in order to find the solution, we take a few steps, we converge to the solution. After several rounds of iterations, we will converge to the solution, and hence it's called an iterative method. And the fourth method that we looked at is the use of power method to obtain the eigenvalue and eigenvector of a system of linear equations. Okay, after which we will start to look at this method called the finite difference method. After we've looked at the boundary value problem, we will then look at the three classical partial differential equations, which we will use finite difference method to solve. Now, let me introduce to you the key characters in this method. Now, although the word Gaussian is used in this method, Gaussian elimination, ascribing the method to the mathematician Johann Carl Friedrich Gauss, history has it that the method itself, the elimination method, has existed many years before. In an ancient mathematical text edited by Liu Hui, there are some impressive treatment of how the elimination method was used to solve a system of linear equations. Now, this textbook called the 九章算术, the 9 chapters of mathematical art. As you can see here, this is a reproduction of the document. Now, although most of us can't read Chinese except those who can, we have the benefit of Google to help us translate this page. And what it says is actually this. There are 3 grades of grain: top, medium, and low. 3 sheaves of top grade, 2 sheaves of medium grade, and 1 sheaf of low grade are 39 dowels. The dowels, it's probably the currency used during that period. And as you can see here, there are 3 variables, right? The first is the top grade, second medium grade, and the third low grade. So you can look at this as if they are x1, x2, x3, or x, y, z, for example. Okay. Now you can start to see where this is going because we will see another 2 more situations which you can form linear equations. Okay. So the second one goes like this: 2 sheaves of top grade, 3 sheaves of medium grade, and 1 sheaf of low grade are 34 dowels. And the last, 1 sheaf of top grade, 2 sheaves of medium grade, and 3 sheaves of low grade are 26 dowels. So the question that they wanted to answer was, how many dowels does 1 sheaf of top grade, medium grade, and low grade grain yield respectively? So it is really a system of linear equations, okay, one from each of these situations, which you would like to solve for the unknown value of the grade. Now, the method to solve it has been demonstrated in the 9 chapters of the mathematical art. And it's very similar to what is written here. So you can see the 3 equations are given on the bottom left-hand side of the slide. And as you can see that the system is systematically reduced to a form whereby the unknown can be obtained one step at a time, okay, yielding the result for the x, y, and z. Now, what other examples are there where this method of solving for systems of linear equations can be useful in engineering? So in this slide, what you see here is a truss bridge, okay, based on the equilibrium condition at every point on the truss bridge. So a structure will be composed of many hundreds of these linear equations, forming a system of linear equations. So in the case where we can generate a system of linear equations, and we have a method to solve the system of linear equations in a systematic way, that will be very helpful. Now, here are several more situations where we can generate a system of linear equations. For example, in the first case, where the mass conservation law can be used, can be adopted for each of these reservoirs. Okay, so from this system itself, it is possible to generate a system of 3 linear equations from which we can use methods such as Gaussian elimination to solve. Now, here are some further examples where systems of linear equations can be generated. So in any situations, in any engineering situation or applications where systems of linear equations can be generated, we can use methods such as Gaussian elimination to solve them. Now, in civil engineering, the study of structural analysis and the use of slope deflection equations allow us to produce a system of linear equations to solve for the various displacement of nodes on this structure, for example. And frequently they are expressed in a matrix form like this. You have a huge matrix A called the stiffness matrix, okay, multiplied to an unknown vector. These are the unknown displacements or rotations, either lateral displacements or rotations at certain nodes where there are degrees of freedom. Okay, and using a method like Gaussian elimination, we can solve for the unknowns. Now let's consider a system of n linear equations. This is a general set of linear equations. Now, there are 3 operations you can perform in the Gaussian elimination method. The first one is you can multiply any number to any equation and then replace that new equation to the old equation. Okay, you can simply multiply that. After multiplying to an equation, you can add or subtract to or from another equation, and the resulting equation can be used to replace the old equation. Okay, and then lastly, you can swap equation. You can take equation number 1 and swap it with equation number 2, or swap it with equation number 3, etc. So these are the 3 operations that you can do in a Gaussian elimination method. Now, before we jump into the Gaussian elimination to solve, maybe we just take one step back and do a very simple set of linear equations. So what you have here is 2 equations. The unknowns are x1, x2. Okay, so just looking at this, you can easily solve for x1 and x2, right? By maybe even substitution, you can do it. You might even use the graphical method, since each equation represents a straight line, right? If this is a system, it must cut somewhere, all right? The point where they intersect will be the solution of your system. So, so apparently here the solution is x1 is 4, x2 is 3. And what does it mean when you say this is a solution? Right? So when you say solve this system of linear equation, And okay, somehow we manage to solve it and we get this answer. So what does this answer mean? This is the solution to the equation. What does it mean? Well, it basically means that these are the solutions that will fulfill the equations, every equation in the system, right? This is the only unique solution because there's only one intersection here. So for two equations, very simple to visualize. How about a three-variable equation? Three equations here, three equations, three unknowns. Now, when we think about the graphical method, what does this first equation mean? There are three variables, okay, x1, x2, x3. This is no longer a straight line, but rather a plane, a flat plane, a surface, right? So each one of these are surfaces. So the cutting of the first and second surfaces, when you put two surfaces cutting together, if they're of the same system, you will get a line, right? The solution of that, of those two planes is a line, right? And finally, you have one other flat surface, which is the third equation, cutting through that line, you will get a dot, right? So eventually you will get a solution which represents the coordinate, the 3D coordinate of this system, which is x1, x2, x3. Now that is using graphical method or even substitution. Now let's take a look at how we solve this same equation, this three equation system using using Gaussian elimination. Okay, so first of all, when we have that equation, the first step is to convert the linear equations into a matrix form. So now you should be able to do this conversion. If you are unfamiliar how to do it, you should try to look at this example, maybe, okay? So the idea is if you can convert it properly, and if it is correct, then when you do the matrix multiplication, you should get back to the same. For example, so 4 times x1 plus 3 times x2 minus x3 equals minus 5.7. Okay, so that should be correct. So in other words, if you have successfully converted the system of linear equation to the matrix form, then all will be well. Okay, so but just to be careful, you can just quickly do a mental multiplication, matrix multiplication, to make sure that all the numbers are correctly populated here. So you have the matrix A here, which consists of all the constants, all the coefficients, and then you have a vector x, which is the unknown, right? x1, 2, 3, these are the unknowns. And then finally, these are the constant on the right-hand side of the equation. So when we would say we want to solve this side of equation, we are trying to determine this unknown here. Okay. Now the first step in Gaussian elimination, other than transforming it into this matrix form, the first one is to rewrite the matrix equation up here in this A hat. We call it the A hat form. All right. This is like the combined, or we call it the augmented coefficient matrix, which is simply a shorthand. There's nothing mathematical about this. This is just a shorthand, whereby on the left-hand side of a line that you draw, on the left-hand side, that is simply the A matrix. And then on the right-hand side is this constant here. So the reason is we don't want to keep writing x1, x2, x3 all the time. You know? So this is simply a shorthand. So it looks like this, okay? And the next step is to convert, all right, to convert this square matrix here into a form which looks like this. Now, this is what we call a echelon form or upper triangular form, or there's another word called the reduced form. Okay, so there are many words to describe the same thing. You can choose any of it, but I like to use the word echelon because it looks like you know, our National Day parade. Well, this year is not the same as before. So you have this plane flying in echelon form. That's basically what I wanted to say. Okay, so it looks like this upper triangular matrix. So we need to get rid of those numbers. Okay, so we need to get rid of these three numbers such that they become 0. So it looks like this. Okay, so if you can get to this form, half the battle is already won. Okay, so let me just skip this first. This is just to say that this A11, A2 to A33 cannot be a 0. Okay, later we will see why that is important. But for now, we just want to see how we can convert a fully populated square matrix into this general reduced or echelon form. Okay, so we start with this, right? This is our original augmented matrix with all the numbers there. So let's try to get rid of the first zero here. Sorry, the first number here. We want to convert this into zero. So how do you convert this to zero? Now, you can try to do, you know, you use your ingenuity to try to figure out how to get this to zero by multiplying and then subtracting, but we are not going to do that. We're going to follow a systematic procedure, right? The systematic procedure here is this. So the number that we want to make zero, okay, this is equation number 2. We're going to multiply a special ratio, a special fraction to the equation, to the top equation, to the diagonal equation, which is in this case E1. Okay, we're going to multiply a certain fraction to this element here, okay, such that when you multiply and then subtract it from the equation that you want to make zero, it will give you a zero. Okay, so this fraction here is actually a ratio of the number you want to make zero, okay, over the diagonal element or the pivot element. The pivot element is the element at the diagonal line right on top of the number you want to make zero. Right? Sounds really confusing, right? So let me just say that again. So this is the number we want to make zero. The pivot element is on the diagonal line. This is the diagonal line, which is the number, the pivot element of the diagonal line, right? This is the one. This is right on top of this, okay? This is the pivot element. So the ratio is the number that you want to make zero, which is 5, divided by the pivot element, which is 4. So this is the ratio that you will come up with. So you have a 5/4 ratio. Now this 5/4 ratio, you multiply to the pivot equation. Okay, this is the pivot equation containing the pivot element. Okay, so you multiply that, and then subtract it out of the equation that you want to make zero. All right, so this will be E2. So it's E2, this equation here, minus a fraction, which is the number that you want to make zero divided by the pivot element. Okay, multiplied to the E1. Okay, so you minus that, you end up with a 0 over here. Now, the only way for you to be convinced of that is for you to literally go and work it out. You have to multiply equation 1, okay, with this fraction, which is simply the ratio of the number that you want to make zero, which is this, divided by the pivot element. The pivot element is right on top of the number you want to make zero. Okay, so it's going to be a 5 divided by 4. Okay, use this fraction, multiply it to the pivot equation, subtract it out of the equation that you want to make zero, or the number that you want to make zero. Okay, so it's E2 minus the ratio times the E1 will give you this. Okay, so you should take some time to convince yourself that this is so. So this will be our new equation, E2. All right, so we have successfully converted this number into 0. Okay, so we are on our way to making this square matrix into the echelon matrix. Now, the next number that we want to make 0 is this one here. Currently, this is 1. Now, how are we going to make this 0? Use the same method, whereby we need to find that fraction. Now, that fraction is the number that you want to make 0, which is 1, divided by the pivot element. The pivot element is always on top, but it has to lie on top of the diagonal. So in this case, it's still 4. Okay, so it's 1/4. So this is the fraction we need to multiply to the pivot equation. Okay, and then subtract it out of the equation that you want to make 0. So this is the equation you want to make 0. So you subtract it out of the E3. So it's E3 minus 1/4 E1, and you will get this equation. Okay, so you see that this method here, this whole thing about multiplying a particular fraction to the pivot element and then subtracting out from a particular equation. This is very standard. Now, the reason for this strict method, you have to do it strictly, is because numerical methods are actually meant for computing. We want to enter into the software a certain step, an algorithm, a method, a step-by-step procedure into the computer so that the computer can do it exactly as you have programmed it to be so. The computer doesn't have to try to figure out on its own way, some unknown way to solve it, right? That's not what we're going to do. We are trying to get the computer to do a certain fixed step such that you can blindfold somebody and just follow the steps and the answers will be produced. Okay, so that's the method. Okay, so maybe just let me pause. I've got two questions. Okay, the first question is, what if the pivot element is 0? Excellent, very good question. In fact, this is what I was referring to in the previous page, right? Where we said that the diagonal element, or rather the pivot element, cannot be 0. So if you divide a pivot element with 0, you will be in trouble because you end up with a very big number, right? So you cannot have a 0 in the pivot element. How do we go about solving it? The answer is to do swapping. Okay, later I will show you how to do the swap. The equation that has this problem where the pivot element is 0, you need to swap it with the equation further down, the next down, the nearest equation downwards, do a swap, and then that should solve the problem. If that doesn't work, you go one step further down and do the swap, and hopefully that will solve the problem. Okay, so very good question. And then the next question is, the pivot element is the element that is lying in the diagonal and above the element that is to become 0. Correct, that's right. The pivot element is the element right on top the number you want to make 0, but it has to be on the diagonal line. Okay, so the example will be clearer when I continue. Okay, right. So another last question, what does the line divider represent? That line is just a drawing, it's just a shorthand, it's just to separate the numbers. All right, so we just want to draw it there so that you don't mix the numbers up, that's all. There's no mathematical meaning. Okay, great, thank you for the question. So now using this two operation that we have done, we have successfully converted these two numbers into 0. Right? And then finally, we have this number to convert to 0. Okay, just ignore that for now. Just ignore this writing. Now, so this final stage here where we want to convert this number into 0. And the step as previously, we need to find that fraction, right? And that fraction will be this number that you want to make 0 divided by the pivot element. Now, where is the pivot element? The pivot element is the number on top, but has to rest on the diagonal. So it's not 3. The number is this. This is the number resting on the diagonal. This is going to be the pivot element, the denominator, so to speak. Okay, so you have a minus 1.75 divided by minus 2.75. So that's going to be the fraction that you need to multiply to the equation. What is this equation? The pivot equation. Multiply it to the pivot equation. In this case, this is our pivot equation now, right? This is our pivot element, and this is our pivot equation. Multiply this fraction to the pivot equation. Okay, subtract it out from the equation that you want to make 0, right? So the equation will make 0 with this number here. There is E3, so it's E3 minus this, all right? And you will get this answer. Okay, so please take some time to work this out later on after the class on your own to see whether you can get all these numbers correct. So if you have successfully done all these 3 steps of converting the square matrix into an echelon form, so you have this 3 looking like this, right? So this is echelon form. So what use is this to us? Okay, well, if you convert it back to equation form, it might be easier to see. Although maybe after a while, you will also recognize it is easily solvable from here. But if you cannot see here, we convert it back to an equivalent equation form. It looks exactly like this, isn't it? Okay, so you can see that straight away equation 3 can be solved for x3 immediately. x3 is just this divided by that. And doing a back substitution, we can determine x2, which is 9.925 minus 4.25 times x3, which we obtained just now. So we can obtain this. And then finally, you can get x1. So by a process of back substitution, we can obtain the solution for this system of linear equation. Okay, right? So in fact, that's all. That's all for Gaussian elimination. The next few slides are simply the more examples. Okay, so there was a question. Okay, so somebody asked one question. Let me read it. Prof, can we reduce further until the augmented matrix is reduced into an identity matrix where the diagonals is 1? There is no necessity to do that. Okay, all we want is reduce it to this form whereby it is the echelon form. The reason is we want to make at least one of this equation with only one variable, one equation, one variable. You can start to solve that. That's the whole purpose. Okay, so you don't have to do any other things. In fact, Gaussian elimination, that will not be Gaussian elimination. Okay, so this is Gaussian elimination, simply like that. Okay, so let me just proceed on to the next example. Okay, not example, rather the pitfall. So this is referring to the question one of you guys asked about the pivot element being 0. So if you see here, this fraction here, as we say, we need to divide the number that you want to make 0 divided by the pivot element. The pivot element is this element here. So if this pivot element is 0, then you will have problem, right? And this is how you form the fraction for the second number, or rather the second column. The number you want to make 0, let's say you want to make this 0, okay? You have to divide by the pivot element. The pivot element is on top, but it has to be resting on the diagonal line. Okay, in this case, it's A22, not A12. Okay. So this is a general form to say that the fraction comprise the element that you want to make 0, whatever that is, wherever it is, divided by the number on top, but it has to be resting on the diagonal. This is actually on the diagonal, all right? This will be a AII. Now you can see that it is in the form of IIIJ because it's easier to do programming later. This is just a general form of doing it. Okay? Right, so I think that's what I've just said just now. The pivot element has to be non-zero. Okay, so let's take a look at an example where the pivot element is a 0. What do you do? I gave a very quick answer, whereby you need to do swapping. Once you do the swapping, you will get rid of this problem. So let's say you have this 4x4 matrix here. Okay, let's do it step by step. So for the first one here, okay, so there's a 0, there's a 0 right here, right? I didn't see that. Okay, there's a 0 right here. So as I say, you need to, what do you call, interchange, swap the equation with an equation further down. The nearer, the nearer, the better. The next nearest equation below the equation that has problem. So this equation has got problem, right? So if you, let's check the first equation below it. Okay, so if we do a swap, you can see that this number here will replace this, right? This whole thing will swap. So we will not have this pivot element having a 0 number there. So that's what we will do. We will do the swapping. You can see that equation 2 and equation 3 is just simply swapped. Okay, so straight away you will not have that problem anymore. Okay, so one of you have got a question. It's a very quick one. What if no matter how we swap a diagonal number is 0? Yes, very good question. It can happen where you may have to swap twice and even 3 times. And if let's say you swap to the end of the row and it still doesn't work, you have to go up to the first one. And if it still doesn't work, then the equation cannot be solved using this method. Okay, can you understand? Okay, so of course in exam situation, it can be solved. Well, maybe I shouldn't say that. Maybe I may put a trick question and see whether you can solve that or not. Okay, so in any case, you just have to do the swap when there is the pivot element is problematic. Okay, so this is one example. Okay, a quick question. Why can't we swap E2 with E1 first? Okay, good question. Now, as I mentioned just now, the method is very strict. So the Gaussian elimination method requires us to go down and not up. You got to go down to equation 3 and then equation 4. And then if it still doesn't, then you go back to equation 1. Okay. One quick question again. Does that mean that this Gaussian elimination method, it is up to my convenience how I can arrange the equation in order? Very good question. Now, you have to start with the given sequence, right? Let's say the question is in a given sequence, you got to start with that. You don't arrange it according to how you want it first. The equation given is the set order, the set sequence. So you base on that. Okay, so hopefully that answers your question. Now, let me quickly move on. Once you do the swapping, you can continue as per normal. Okay, so these are just the general way of expressing Gaussian elimination. You can see that this is the general form of an echelon format. Okay, so anything below that diagonal line, that has got to be 0 in order for you to proceed to the back substitution stage in Gaussian elimination method. Okay, what you see down here at the bottom of the page is simply the equation form, equivalent equation form of this matrix form, right? So you can easily see in the last equation, you can easily obtain value of xn, right, which is the constant divided by the coefficient. Okay, and then doing back substitution, you can eventually obtain the values of x1 all the way to xn. Okay. Okay, somebody asked that question. I think let me proceed first and then I'll attend to the question. Okay, so using back substitution, as I say, you can obtain the rest of the other variables. Now, this page is summarizing what you are actually doing. So, for example, if you want to obtain the value of xn, which is the last equation, it's simply the constant divided by its coefficient, right? It's the constant, whatever that is, divided by the coefficient here, right? And then to obtain the next one, let's say the second last equation, it's simply the constant here minus the whatever sum of is the product of the coefficient times the xn. For example, if you see here, this one, we're trying to solve this, xn minus 1. So in order to solve this, is simply the constant minus away this value here, okay, which we already obtained the value of xn from here. We can substitute it. The coefficient is known. So it's constant minus whatever this is, and then divided by the coefficient of this unknown variable. Okay, so it looks like this. Now, if you put it in a general form, what it says is that, let's say this is any particular equation, is simply the constant on the right-hand side of the equation minus away a summation of everything that you have obtained prior, right? So this all these values are obtained prior. Okay, so that will include all these terms, and then finally divided by the coefficient of the unknown variable that you're looking for. Okay, so this is the general form of this entire thing. Okay, so this is example 2. I will leave this example for you to do. Okay, so, but first of all, the step, you must know that the conversion to matrix form has to be done carefully. Okay, so you can write it in this form. This line, as I say, is just a shorthand, and the answer is already given there. Okay, so you try to work it out on your own. The solution, the full solution is given here. Now, this is an important equation because we will use this same equation again in another method, right? Called the LU decomposition, which I will cover next week. Well, thank you very much for joining me in this lesson and hope it has helped you. If you like this video and found this useful, please press like and hit the subscribe button for further lessons next week. I've put up a link to the Excel implementation at the top right hand corner. See you there.